In second case, we consider cos theta is equal to T2 minus T1 divided by T3. Suppose T2 is less than T1. See here, suppose the value of T2 is less, then whole product is negative. It is negative. That is, we can say that cos theta is negative. Cos theta is negative, that is theta is obtuse. Theta is obtuse. Now in third case, suppose this T2 minus T1 is equal to T3. See, both are same. The cos theta is equal to 1. Cos theta is equal to 1, and we can say that this theta is equal to 1 for, or theta is equal to 0 for pure water. Pure clean water. Now the last case, in last case, suppose we consider this T2 minus T1 is greater than T3, that is, it is greater than 1, and liquid drop cannot be formed. It is impossible to form a liquid drop. It is impossible to form a liquid drop. These are the 4 cases for this angle of contact. In case of mercury, it is the same assumption. This is the T1. It is the force of surface tension due to the solid and liquid interface. T2 is the force of surface tension between solid and air interface. Then this T3, it is the force of surface tension between this liquid and air interface. Again we get same equation, T1 plus T3 cos theta is equal to T2, and we get cos theta is equal to T2 minus T1 divided by T3. This is all about the angle of contact. Now we see excess pressure, the next topic. Excess pressure across free surface of liquid. Across free surface of liquid. Now suppose we consider the free surface of liquid the upper surface, free surface is plane. Then see, the surface is plane. This is the force of surface tension Ft. This is again force of surface tension Ft. Now we consider the point A here, and this is the point B. Then see, in this case, this is plane surface. These two forces are equal and opposite. There is no pressure difference. Thus we can say that pressure at point A is equal to pressure at point B for plane surface. for plane free surface. In case of the plane free surface, the force of surface tension, it is equal and opposite, therefore pressure is equal to same, there is no pressure difference, that is pressure at point A is equal to pressure at point B. Now in second case, suppose we consider the liquid surface, it is like this convex surface. For example, we consider here mercury. The free surface of liquid, it is convex, and see here, this is the force of surface tension. That is, we can draw here tangent to this surface and here again tangent to this surface. Now see, suppose this is point A, this is point B. Now this is the, see, this is pressure at point A, or we can say force at point A, it is vertically downward. It is vertically downward. Now this is one pressure, this is one force, this is another force. The resultant, by the law of parallelogram, the resultant force is given by this diagonal and it is maximum. That is Ft, it is also in the downward direction. Thus we can say that Fa plus Ft, it is maximum. And pressure is also maximum at point B. Thus we can say that pressure is maximum at this point, that is PB greater than PA. In this case, at the concave side, the pressure is maximum at the convex side, at this convex side. Thus we can say that pressure at concave side is greater than the pressure at convex side. Now we see the convex surface. In case of concave surface, see here, suppose here the free surface of liquid, it is concave. Again, the concave surface, it is for kerosene, impure water. These are the examples. Then the free surface of liquid, it is concave. Now suppose this force of surface tension, it is denoted by this tangent, and this is the force of surface tension denoted by this tangent. This is the point A, this is the point B. Now in this case, these are the forces, and the force of surface tension, it is in the upward direction, while the force due to atmospheric pressure, it is in the opposite direction. Now in this case, this Fa, or we can say Ft minus Fa, it is less, and the pressure at this side, it is, suppose at this point it is developed, the pressure is less, and we can say that at concave side the pressure is larger than this point B. Thus we can say that is pressure at concave side, if here the pressure is greater than this point, and we can say that pressure at concave side, it is greater than the pressure at convex side. Now we consider the next topic, explanation for formation of drop. Suppose we have the drop, explanation for formation of drop. formation of drop. Suppose this is the drop, then Pi is inside pressure, the radius of drop it is R. Now due to the pressure inside this concave surface it is greater and the outer layer displaced through some distance, and we can say P outside, pressure outside, this extended through this delta R. Therefore we can see that Pi minus P0 it is the excess pressure. Now see, for we consider first, that is A1 is the initial area, and initial area we consider it is the 4 pi r square. Now the area is increased and the final area it is 4 pi r plus delta r bracket square. Then A1 minus A2, we can expand this bracket, that is 4 pi into extend or expand this bracket, it is r square plus 2r delta r plus delta r square. Then arrange the equation, 4 pi r square plus 8 pi r delta r plus 4 pi delta r square. Then delta r is very small, thus we can say that it is neglected, delta r square is neglected. Then we get increase in surface area, A2 minus A1 is equal to 4 pi r square plus 8 pi r into delta r minus value of A1 is 4 pi r square. See, these are the same quantity but the sign is opposite, these are cancelled. Therefore increase in surface area is equal to 8 pi r delta r. We can write dA is equal to 8 pi r delta r. Now we know by definition the surface tension, or we can say surface energy, or we can from definition we can write T is equal to force per unit length, and here we can write that is for surface energy is equal to surface tension into increase in surface area. Surface area energy dW is equal to T into, substitute this value, that is 8 pi r delta r, equation number 1. Then see, dW is equal to 8 pi r delta r into T, equation number 1. Now from definition we can write, we know the pressure is equal to force per unit area. Here pressure is Pi minus P0 force F, excess force, and area is suppose dA. Then excess pressure we can write here force, excess force is equal to Pi minus P0 into dA, and it is Pi minus P0 and the area is 4 pi r square. We know dW, work done, it is equal to force multiplied by displacement. Then force is here, Pi minus P0 into 4 pi r square, and displacement is delta r. This is equation number 2. From equation 1 and 2, from equation 1 and 2, see, this is work done, this is also work done. Then we can say that T into 8 pi r delta r is equal to, we can write this second equation, Pi minus P0 into 4 pi r square into delta r. Delta r gets cancelled, pi is get cancelled, r is get cancelled here, and we get Pi minus P0 is equal to, see here 4, this is 2, that is 2t divided by 1 r here, that is Pi minus P0, it is 2t minus 2t divided by r, and it is excess pressure. It is excess pressure for drop. If we consider the bubble, for bubble it is Pi. For bubble we can say it is Pi minus P0, it is 4t divided by r. In case of bubble, there are two surfaces and we get excess pressure is equal to here 2, here 4. Therefore, excess pressure is Pi minus P0 is equal to 4t divided by r. Now we see the next topic, that is capillary action.